Hey, welcome back. This is our last section of Chapter 3. We're going to talk about doing some transformations with different models that might not be linear. So far we've learned how to analyze relationships between two quantitative variables that showed a linear pattern, usually like when we're dealing with scatter plots here. When two variable data showed a curve, we just talked about, we said it's nonlinear. But we must develop a new technique for finding an appropriate model. So this section describes several different transformations that we can make with data that can straighten a nonlinear pattern so that we can do all these things that we've done with the linear ones. So let's just say we have this situation here. Okay? Imagine that you have been put in charge of organizing this fishing tournament in which you get prizes for the heavier fish that you catch. So you know that a lot of the fish that are caught are going to be caught and released. But you're also aware that measuring the weight on a boat is not super accurate because of the different movements of the boat, the waves and whatnot. It's usually not accurate. So so oftentimes people will measure them based off of the type of fish and the length. And there's a relationship there. So we have below a scatter plot of data from several rockfish of several sizes comparing length and weight. And as you can see here, it's not linear. It's got a curve to it. Now, if we have a curve to it, we don't want that. We want to have it to be linear. We'd ideally like it to be linear. But if it's not linear, right? Not quite. So, one way that we can make this linear, that they found in this example to make it linear, is to change part of it. If you look on our computer printout over to the right here, and if you look on the graph, we are cubing every weight. So if you think about weight and length, so weight is like a three-dimensional thing. You got length, width, height, whereas length is just one dimension. So to get them on the same level, you could cube it, and then they're both like three-dimensional, right? And then look what happens. It's a very linear relationship. Now you can see that from the labels there. You can also see it on the graph, or sorry, on the computer printout where it says weight versus length cubed. You can also see right here the x variable says length cubed. So those are all there. So because the transformation made the association roughly linear, we use computer software to perform a linear regression analysis of y equals weight versus x equals length cubed. So give the equation the least square regression line and define any variables. So if I'm looking at that, my least square regression line now is going to be slightly different. So I've got a couple questions here. My equation will still be y hat because we are predicting. From the computer printout, there's 4.0. Just want to make sure 4.066, and then the slope was 0.0147-ish. So 4.066 plus 0.0147 x cubed. It is length cubed. That is our new equation. Defining the variables, I would have to still define x as the length of a fish. So if I tried to define x cubed, it would just be the length of the fish cubed. So I can still say x is the length of the fish, y hat is the predicted weight. And I might want to add in that this is in grams, and the length was in centimeters. So now that we have a model that is appropriate, that showed a linear thing, we can actually use all the same things that we've done before with linear models. Like question 2, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part A to predict the fish's weight. So all we'd have to do is still plug in for x and get a value. It'd be y hat equals 4.066 plus 0.0147 times 36 cubed, which if you put it in your calculator, you should get about 689.9 grams. Okay, for an FRQ, you'd want to put that into a sentence. But this is a common thing that you might be looking at when you have something that's nonlinear. Now, you might be looking at this and say, well, to make it so that they're both three-dimensional, we cubed the length. Could you do the opposite? Could you make it so that they're both essentially one-dimensional and also form a linear? Why, yes, you can. So there's another way. If you cube root the weight, now you're taking a three-dimensional thing and bringing it down to one dimension, and we can compare it to length. It does change a few things, but now we see we have cube root compared to length, and we can take a look at our computer printout as well and see some other similar things. Like here it says cube root of weight versus length, and we still have length there as your x value. Different equation. So it says give the equation of the least square regression line, define any variables. We're going to be doing the same thing, except now it's the y value. So it would be the cube root of y hat. You could probably put it on the inside or the outside. I think the hat part is typically on the outside in general, so I'm going to put it on top there. And then we are still given the b value. This is negative 0.02204. Again, that's right here. This is the, sorry, that was the a value. A value, b value right here, plus 0.2466x. All right. So we have a new model. We could answer the same question or a similar question based on this. I guess what's a 36 centimeter one? We would say all this equals negative 0.022 plus 0.2466 times 36. You get the cube root of y equals about 8.87. And to get rid of that, you'd cube it to cancel out the cube root. Sorry, cube, not squared. And you get an answer of about 600. So I get y equals 694.61 grams. Now that is slightly different than our last answer. Our last answer was 689.9 grams. This is 694.61 grams. In the same ballpark, but there might be some slight differences depending on the model that's used. So, now that we've talked about a couple different ways to model something that's nonlinear, like powers and roots, we can predict things about these rockfish, but we still expect it, the power model of the form weight equals a times length squared based on geometry. So instead of using all this stuff with lengths, with powers and roots, the AP curriculum prefers to transform data using logarithms. Okay, that's just something that's done, and we want to talk about how we're going to do that. So transforming with logarithms, if you suspect a power model, that's one of those models where you have like y equals x squared, for example. Then you would take the log or the natural log of both x and y. If you suspect an exponential model, that's where the x is actually in the exponent, so y equals, I don't know, some number, 3 to the x power. That's going to be just taking the log or the natural log of y. Now, when it comes to the AP exam, transformations usually will be done for you already. You need to know how to find the least square regression line, define the variables and numeric values, and use the least square regression line to make predictions. Okay? So, before we do anything with logarithms, let's review some things with exponents and logarithms. Exponent rules, back to algebra. If you have x to the 12th power times x to the 4th power, you can simply add those exponents. You keep the base and add the exponents, and you get 16. So it's like taking 12 plus 4, keeping the base of x. Okay. I'm sure you've also learned when you have a power to a power, that is like the distributive property. You would multiply, and you would get, well, it'd be x to the 12 times 4 power, which is x to the 48th power. Negative exponents, if we have a negative exponent, we can make it 1 over that to make it a positive exponent. Now, there is some relationships between exponents and logarithms because they're kind of inverses of each other. So let's review some things about logarithms. Log base A, remember this is just a base. Can be different bases, but generally if it just says log, it's base 10 of B equals C. This is natural log and that always means that it's base E. What the heck is E? Well, it's on your calculator, it's a number, and it's used with natural logs. So, if you look on your calculator, you can find the letter E, which is the number E, above the division symbol. So if I do second division symbol, I get E, and it gives you about 2.718, yada yada yada. Kind of like pi, it's a irrational number. So we're going to use that with logarithms. All right. So if I have log of 4.5 equals x, I don't want log in this. If I'm trying to solve to get log away, I'm trying to just solve for x. I know that log is just generally a base 10. So what I can do is I can make the base 10. But then I have to do it to the other side. But that cancels out log. The log and the base and the 10 cancels each other out when they are exponential like that. So I'm left with 4.5, and I'm left with 10 to the x power. And then I can solve it for x if I want. I can go from there. Now if I have logarithms on both sides, same deal, it's just going to be base 10. But I need to take this and say 10 on both sides cancels out here. It also cancels out here, and all that's left is 6 equals 3 plus 5x. And then you can solve it for x. Now with natural logs, it's base e. So if I want to get rid of a natural log, I do base e to cancel it out. I do it to the other side, which leaves me with x equals e to the 4th power. And I can go on my calculator, I can figure out what e to the 4th power is and get the actual number or get a rounded version of that, which you're going to get somewhere in the, I don't even remember. But you can get an actual number for that. This last one is probably the most work because we need to do natural log to get rid of that. And I need to do it to this whole side. But when I do it to this whole side, I can use kind of the reverse of what we did earlier with exponents. When you added exponents, like this one, this very first one, this was 12 plus 4, which got us x to the 16th power. If I want to go backwards, it's the same as splitting up that base into the two things that were added and then multiplying the whole things together. So here, it would be e to the 5.6 power times e to the natural log of x. I'm going to put actually in front. You can switch that around. And I'm going to put that 4 outside of parentheses just because it'll work out nicer in the end. So I'm currently left with y equals all that. Well, e to the 5.6 power is a number, so I get y equals, it's about 270.42 times, these cancel out, so whatever's left is my, like the variable is my now new base to the 4th power. Okay, so when that cancels out, the whatever was with the natural log becomes your new base because those cancel out. but the 4 is still an exponent. So now this is a power model. Okay? As a power model, I have x to the 4th power. That's how I'd write that equation. And we're going to be doing some of that. Moving things around using natural logs. So, let's jump back to this. All right, I have an example here that is comparing weight and length and weight. It's the same problem that we did before, but we're using logarithms instead of our power models or our root models. So, if I look at the data now, if I did log to both the weight and the height, or sorry, the length and the weight, sorry, I can see in this that we did log on both. So this is a logarithmic one. I can also see on the computer printout here, and then it says log weight versus log length. We have log on both of them. You need to note that. That tells me that there was a transformation done. Also, if it's done to both, this is a power model. I like that last one we just were solving. Now, based on the output, explain why it would be reasonable to use a power model to describe the relationship between length and weight. So why can we use this power model with logarithms? Well, we did talk about how it straightened out the line, but basically, straightened out the line and the residual plot. When we were looking at a residual plot, we want it to be scattered, and we want it to be kind of even on either side. This is scattered. There's no clear pattern or anything in there to show that it's nonlinear. So this really did become linear. Given an equation of the least squares regression line, be sure to define any variables you use. So if I go back up here, I have my A and my B, just like I would any other time. But we're just going to be using log of weight and log of height. So how I would write that then is the log of y, which was my weight, hat, that's predicted, equals negative 1.8944 plus 3.0494 log of x. Okay, so we're using log instead of x and y instead of just regular x and y. And we have our new equation. Now we can still identify it as x is our length, or our, fish length in centimeters. We can still say our y hat is our predicted weight. But if we want to also define the numbers and numeric values, we would have to say a little bit different. We would say that negative 1.8994, or 944, I don't remember what the number was. Maybe it's 994. 994. So I just wrote it wrong here. That is the predicted log of the weight when the log of the length is 0. That is important to know. With the numbers, we do have to state that, because that's what we're doing. That's where these numbers are coming from. And this is, again, the predicted increase in log of the weight for every added log of the length. Okay? Now, we can use this model then to predict. Again, we use that 36 centimeters long. Hopefully it's in the same ballpark as our last ones, but maybe not. Maybe a little bit more accurate. We'll see. It says, suppose the contestant in the fishing tournament catches an electric rockfish that's 36 centimeters long. Use the model from part B to predict the fish's weight. So we had log of y hat equals that negative 1.8994 plus 3.0494 times 36. So we're actually going to do log of 36 there, sorry. Okay. Now, if we want to actually solve for y, we have to do some of that skills that we just did before. This is regular log, so it's going to be a base 10. So to cancel out the log, I do base 10. I have to do to this whole other side. And when I do it to this whole other side, I would be doing that to this whole thing. So I can break it up and do negative 1.8994 times 10 to the all of that. So I'm going to, like we did earlier, I'm going to put that log 36 with it so I can cancel that out and leave the 3.0494 on the outside. That gives me y hat equals this value, which is like, if I plug in my calculator, it's 0.013 times 36 is my new base to the 3.0494 power. Use the calculator. Get your answer with all that. You don't have to do any of this by hand. You can use your calculator. It ultimately should get us 702.08 grams. That is our estimate from this. Now, is that close to our other estimates? If we go back, we end up getting like a 694, and we got a 689. They're all very similar. They're in the same ballpark, just depending on the model. Slightly different models will give you slightly different answers, but they're all in the same ballpark. Okay. I just want to wrap it up by looking at one additional example. This is with a natural log one. It says here's a scatter plot of the natural base E logarithm, so that gives it away, it's natural log, of the number of transistors on a computer chip versus years since 1970. So years since 1970 is our X. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between those transistors and years since 1970. So one of them is used by the natural log or the logarithm, just the y, which means it's an exponential model. And it's fairly linear. So my argument right there is we use natural log and it's fairly linear. So that is going to be an exponential model. Now, the computer printout, which I'll bring up here, shows some of that as well. It does not clearly show natural log in the computer printout. This one does not have anything on top. It just says the X is our year since 1970. So we need to look at the problem and also the y-axis to find that we're using natural log. But we've got our A and our B. So here's the computer printout. Give the equation of the least squares regression line. Be sure to define the variable. So I would say this is natural log of y hat equals 7.2272, that's from our thing, plus 0.3542x. Now you can define your x and you can define your y. X would be the number of years since 1970, and y would be the number of transistors on a computer chip. So let's do some things with that real quick here. Use your model to predict the number of transistors on an Intel computer in 2020. Now, let's just double check here. Is that realistic to use that? 2020 would be 50 years after So we don't have anything quite that high. It'd be like over here-ish. So it is a little bit of extrapolation, but it's close enough. So let's actually do it. So years since, that would be 50, x equals 50. So if we use our natural log of y hat equals all of what we just wrote down, and plug in 50, we should be able to solve this. It ends up being the natural log of y hat equals, I've got about 24.9372. So how do we figure out the y? This is where we have to use those rules. The base e will cancel out natural log, so I'm going to do base e on both sides, cancel out, I've got y hat. And all I have to do is my calculator, figure out what e to the 24.9372 power is. And then I'm good to go. My calculator actually tells me it is 6.76 E10. You guys remember what that means? That is 6.76 times 10 to the 10th power. It's a really big number. It actually will give you a lot of zeros. It's 6, 7, comma 6, 0, 0, 0, 0, 0, 0, 0, 0. It's moving that exponent over 10 places. So it adds 8. So this is 67 trillion 600,000. 600 billion transistors. Wait, no, it is billion. 67 billion 600 million transistors. All right? So that is how we can use different things to transform a nonlinear pattern to be linear, so we can then use all these things that we've learned about analyzing and using scatterplot data to predict things. And that's section 3.3 in a nutshell on transformations. We'll see you next time.